Thank you, Dr. Patricia, and good afternoon, everyone. Today, I'm going to talk to you about understanding IMRT. This In this lecture, several present slides are taken from Dr. Jerry Batista's IMRT lecture that he delivered in a course way back in 1999 and 2000. You can look that even after 25 years, those are still relevant. And I have made modifications though, but I have to acknowledge that several of the slides are from him. I'll just change my pointer. Okay. Um, so in this lecture, first I will talk to you about what is IMRT, what is intensity modulated radiotherapy, then talk to you a little about history of IMRT and how does the inverse planning work. Then we will go into methods of IMRT delivery like compensators, step and shoot, dynamic, volumetric arc therapy. I may not do tomotherapy now because that may need a separate lecture on its own. First, what is IMRT? IMRT is the delivery of a conformal radiation dose to the patient via fields that are non-uniform, that has non-uniform radiation influence. So, IMRT is basically delivering conformal radiation dose to the patient via fields that have non-uniform radiation influence. This IMRT allows for conformal dose distribution around a tumor while a rapid dose fall off spares the surrounding critical structure. The dose falls off very rapidly once it is outside the tumor, right? There were opinion that the terminology has been very incorrectly established because strictly it is the fluence, not the intensity that is modulated. But however, we have been using intensity modulator forever and it has become the terminology for it. How did this IMRT evolve over the days? I know I have been working for more than 37 years, 38 years now. Actually, when I started, I remember having rectangular fields or square fields. And later on, when radiosurgery came, we went on to circular fields. So, even though the tumors are never square or rectangle, we were using square and rectangular fields and tried to shield the rest of the areas using blocks and things like that. That was conventional RT. Then came the multi-leaf collimators, which made us to shape the radiation beam to the shape of the tumor. And we started calling it conformal radiotherapy. Then the IMRT came, which in addition to conformal beams, it also changed the incorporated the fluence variation, which resulted in very good dose distribution to the tumor and practically or very less dose to the normal tissues and the critical organs. Let us do a small comparison between a 3D CRT and IMRT. 3D CRT is a geometrical conformal radiotherapy, as I said in my previous slide, in which the outline shape of each beam can be controlled, but the fluence was uniform. We also had a concept, even still we have a concept that to deliver a uniform dose distribution to the tumor. All right? And with 3D CRT, we were able to achieve to a larger extent that. But when it comes to IMRT, it adds modulation possibility to the 3D CRT, combines both geometrical conformal beam and fluence shaping. So for example, if you look at the images here, this is actually I have kept 2D, two parallel opposed beams, and even though I shape the beam, I will still include the critical organs here. Even though you change the angle, some dose will be to the critical organ. Then came the IMRT. This is a 7-beam IMRT. If you do this, you can have dose distribution to a tumor like volume which is like this and avoid the critical organ, which is actually middle of the two tumor volumes that you see here. So it is possible to sculpture the dose distribution to the shape of the tumor volume. That is the beauty of IMRT. So the IMRT techniques evolved over years. The first one came up in 1992, which was called Nomos mimic system, and then the multiple static field IMRT technique, MLC technique was introduced in 1994. Then came the dynamic MLC, again the same year, and the scanning attenuation bar technique came around 1995, not very much in use. Intensity modulator arc therapy, IMAT, came in 1995, and I will talk about it a little later, maybe at the end of the lecture. And then the spiral tomotherapy came up, and volumetric modulated arc therapy came up. The spiral tomotherapy came up in 2003, actually, though the concept was developed in 1993, because I was working at London Regional Cancer Center in Canada, where they were one of the beta testers for tomotherapy at the time. So I had an opportunity to look at it, though I couldn't get an opportunity to work with that, how the tomotherapy was started those days. Going into the history of how the algorithms were developed for IMRT, it was the concept given by Brahmi et al. Right? He was solving inverse problem of rotational beam fluence to deliver a uniform dose to a donut-shaped target. I will show you in the next slide. And then in 1984, he first commercial MLCs generated and patented by him, which was later on became a commercial one by Scanditronics. Steve Webb came up with another algorithm, which is an inverse planning problem as an optimization problem that minimizes an objective cost function. I will talk about that also a little later. Then Bonefield et al. Developed an algebraic iterative optimization algorithm, which actually was much faster than what was earlier. So this was also incorporated in several planning systems. Boyer et al. Developed the principle of multiple segmented field IMRT, and then the full IMRT system based serial tomotherapy was introduced, and NOMOS mimic binary MLC and simulated annealing optimization were also introduced later. The concept of tomotherapy was given by Rock-Mackey et al. In the year 1993. So this is what actually the Brahmi's concept, right? Both the concepts I have shown here. Let me look at what is on the right side of my side, or the left, I would say for you. The concept is that wherever the tumor volume is larger, the intensity has to be higher. Wherever the tumor volume is smaller, the intensity has to be lower. Or wherever there is critical organ is there, the intensity has to be lower. This is the concept that he introduced. For example, if you look at, for a tumor volume that is of this shape, you have to have a larger influence here, and the middle, the tumor volume is less, and also you have a critical organ, so the fluence is less here, and then the fluence is large because the tumor volume is large. So when the beam goes to a lateral side or a oblique beam, you can see the same thing being changed to wherever the ray has to travel longer distance, the intensity is higher. Wherever the ray has to travel shorter distance, or there is a critical organ, then the intensity is less there. So this is how the initial fluences were done for IMRT. This is just a basic concept, but this is what we are looking at inverse. You go back, this is the thickness, and you go back and make the fluence accordingly. And he also came up with the donut-shaped dose distribution. You can look at, to achieve that, you need to just close the middle and have radiation fluence here, and then just do a full arc, then you will get a donut-shaped dose distribution. As you can see here, you have dose around a particular tumor, around a particular critical organ. So suppose this is critical organ, this is the tumor, you should be able to do this. This we can do nowadays with any of the beams, any of the linacs that's available. And what is inverse planning? Inverse planning, actually you start out with the dose criteria, then allow the computer to design the beams, right? An important step in IMRT inverse planning is that this is a process by which the optimum intensity distribution is obtained by minimizing an objective function or a cost function. That's what I was telling in the earlier slide also. So you need to, that's Steve Webb's concept, you have a cost function, try to minimize the cost function as much as possible to get a good dose distribution. Here, instead of the planner trying a variety of permutation combination by changing beams, wedges, and beam weights and things like that, right? You can, until you get a dose distribution. Normally in forward planning you keep changing all this, but in this a reverse is attempted, right? You say this is the dose distribution you want and let the system decide what has to be done. And basically, an optimization should involve several things. One is to arrive at an optimum plan, there are different beams available: proton, carbon ions, photon. No, no, ideally, I'm talking, right? You may not be having a machine which gives all this, but ideal condition is that you should optimize like this, or all energies, not just those we have available, right? You should have all energies possible, all possible number of beams from 1 to infinity. We almost have come there. I will tell you why I say that. And all possible ranges of fluence levels, and all possible beam geometry and shapes, all possible fractionation schemes, and so on. So, how do you arrive at this? By optimization techniques. One is you can use deterministic techniques like gradient method or conjugate gradient, linear programming, maximum likelihood, and also iterative method, which is now very common, like simulated annealing, which was given by Steve Webb, where you take a cost function and reduce it, or fast gradient descent method, which was by Thomas Boatfield, which actually increased the speed of optimization. The inverse problem actually has to be two. Let me explain you why I say there are two inverse problems in IMRT. One is to determine the optimized intensity map. First, you need to know what should be the beam to deliver a conformal or dose distribution to a particular tumor, right? So that beam has an intensity map that's referred to as the intensity map. So to generate that intensity map, you do an optimization. Next, you have an intensity map. Now to deliver that, you need to do leaf sequencing. Let us forget this compensator based one for time being. Let us say you are using multi-leaf collimator. So you need to do a leaf sequencing to deliver that particular intensity map. So there are two inverse problems. First inverse problem is to generate an intensity map. Second inverse problem is to generate leaf sequencing to deliver the intensity map. But later on, in the bit or late 2000, people came up with a combination of these two, which is called direct aperture optimization. You don't need to do separately. As the fluence is generated, a direct aperture optimization happens. I'll talk a little bit about this again at the later when we talk about the VMAT. So this was suggested by Shepard et al., an automated planning system in which they bypass the traditional intensity optimization, instead directly optimize the shape and the beam weights of the aperture. Everything was done in one optimization. So how does that optimization work? I have been saying you need to have a cost function and you minimize it. So the idea is to minimize some of absolute differences between the prescribed and the delivered dose. Doctor has prescribed a dose and the planner keeps doing planning. So when they plan, they get particular dose. The difference between the prescribed and the planned one should be as small as possible. So minimize it. That is where the optimization comes. So minimize sum of quadratic differences between the prescribed and the delivered dose. So this is the planned one, and this is actually the calculated, I would say, rather than delivered. Calculated one, the square of the distance should be as small as possible. So minimize a weighted interval dose or maximize the minimum dose to the target. So what is the cost function? IMRT treatment plan parameters are determined by means of optimization procedure with an appropriate cost function. The cost function is a measure of the distance or the difference, I would say, between the prescribed dose and the determined or calculated dose. Cost function actually includes the clinical objectives of the treatment plan. So cost function is a measure of a difference between the prescribed dose and the determined or the calculated dose. It can be based on dose criteria, which is a physical cost function, or it can be based on biological criteria, which is a biological cost function. Biological cost function can be considered more efficient than a dose volume cost function, but only if you are very sure the biological models are known with an accuracy better than the typical one. That is the question. Whether we understood the biological models is a question, right? So, how does it work? I'll give you a little bit about it, not deeper into it. Instead of matching a desired dose distribution, we have to define a cost function. It can be also called a figure of merit. So, what is a cost function? Is the average target dose minus the desired dose plus average OAR dose minus what is allowed by the for the OAR, that is the dose limit. So this is actually the differences. Some of this differences is called the cost function. So how do you achieve that? The cost function should be minimum. To make it the minimum possible, how do you achieve it? You do either do filtered projection or do trial and error, which is an iterative process. That is the steep gradient search or simulated annealing. So when you do a trial, suppose if you go there, you feel that is a minimum, you achieve, but it's not a minimum, it's called local minimum. And then you keep on searching for it till you get an absolute minimum. This is where you have to be there. So this is an equation that's being used for the objective cost function. This is the weightage for each of the beamlet. What they do is for doing this, the beam is splitted into beamlets, right? Small beamlets, and for each beamlet, which will go into a particular voxel in the CT, the dose at that voxel, that is the dose in the particular voxel where there is a OAR or the tolerance dose, right? This is the tolerance dose, this is the OAR dose. Then you see the difference and take the square of the distance, right? And this C is called the constraint operator. This is what I have been saying as the cost function. And this is the weightage for the beamlet. So this is how the objective function or the cost function is determined. And in present day scenario, the optimization is done mostly with a maximum or minimum dose. You say this is the maximum dose or minimum dose, but in a not present day scenario, but I would say earlier, and of course we have changed over from that. Therefore, the dose volume limits were introduced for further improvements. We are not happy with giving only a maximum and minimum dose, but you also want to know this volume of the tumor should get this percentage of dose. That's what we refer to dose volume criteria. So today, dose volume based objective constraint are essential in most of the commercial inverse planning system. The other optimization approach, as I said earlier, instead of using physical dose objectives constraints, you can use biological planning objective, which is effective uniform dose, right? Or we call it UD based inverse planning. UD is the dose that when homogeneously given to an organ or structure yields the same biological effect as given non-uniform dose distribution. So this is called effective uniform dose based inverse planning. Some of the planning system provide you this also. So how the iterative method works, it's a very simple diagram to explain you how it works. So initially you have a beam weights and you compute the dose distribution and then determine what are the update factors. If you are okay with that, then you accept it and then you finish it. If you are not okay with that, you recompute, right? And if it's not acceptable, you go back here, update the factors, recompute, and then come here. Again, you are not happy, it goes back and keeps on doing it till the minimum cost function is achieved. And then once it's obtained, you finish the optimization. So now we learned how the optimization or the inverse planning happens. Now, how are you going to make the leaf sequencing, or how are you going to generate the Fluence map to deliver it? Earlier days, the best way they were using was to have compensators. So physical compensators were used for making compensator as a old study for us. No, we have been using compensator for years. So why not we make compensators to deliver the Fluence map? So the compensators were generated, but using these type of milling machines where you generate a compensator like this. This will give a Fluence map that was calculated using the optimization. So if later on the MLCs came, MLC started using. So this is same distribution developed, generated using MLC and generated using compensator. Compensator actually gives you very smooth dose distribution compared to MLC, because with the MLC you have a restriction on the size of MLC, whereas in compensator you can go sub millimeter and make it very smooth. But there are some issues with compensator. We will, and for academic reason, I will try to explain that what are the issues with compensators compared to IMRT. Sorry, compared to MLC based IMRT. So one is, when you put a compensator, you are keeping some high density material inside. So this brings in beam hardening, right? When radiation beam goes through the compensator made of low melting alloy, point alloy, then there the low energy beams are cut off, you get only high energy beams. There is a beam hardening which will change the beam parameters in the patient. And then the compensator will create scatter, so it increases scatter radiation. You are keeping a now a beam shaping device. So for each beam you have to go in, enter the room and keep the additional device and then take it out. You have to be very careful. You don't use the beam 2 compensator for beam 1. There is a possibility of error there. And then you have to walk in between into the room for every beam. If you have 7 beam IMRT, you have to walk in and remove it and put it in. And all these problems will come. And the storage of the blocks. If you are treating 50 patients, so 50 into 7, so many blocks will have to be stored. It's a bit cumbersome method, right? So then, because we have multi-leaf collimator, then they thought of using multi-leaf collimators for generating the fluence. For example, let me say you have a fluence map here. To generate this, they divided the beam into beamlets. The beamlet size will depend on the thickness of the multi-leaf collimator. You can't make it smaller than the multi-leaf collimator in the thickness direction. You can make it in the lengthwise direction. You can move the MLC even 1 millimeter and say my beamlet is 1 millimeter. But the width of the MLC is 3 millimeter or 5 millimeter, right? So your beamlet cannot be smaller than that 5 millimeter width. Made beamlets, they close the beamlet with an MLC or open it. So they can make small beamlets. So each beamlet can have a weightage. So each point you can change the dose intensity. So this is actually the beamlets that have been made. For example, here the intensity is less. Here the intensity is slightly more. Here it is much more. So this is a much better method, and it's easy to do the calculation also on that. So these are some of the multi-leaf collimators that I have here. This is from the variant multi-leaf collimator. It works, it is attached to the collimator. It is in a bank here. You can see these are the leaves, right? And this has got a rounded edge, like the edge is rounded to reduce the penumbra. Then when you deliver the IMRT with the static or step and shoot, which you all know by now, so what we normally do is, to deliver a fluence like this, you need to create segments. This is segment 1, this is segment 2, this is segment 3. When you deliver all these 3 segments, you will get a fluence map like this. So it is segmented IMRT, you can say, or step and shoot IMRT, you can say. So what we are going to do is now how to generate the segments and to deliver is what we are going to look at. As I said earlier, there are 2 methods. One is step and shoot IMRT. The other one is sliding window IMRT. Step and shoot IMRT is where the multi-leaf collimators go and generate a shape like this, and then the beam comes on and this is delivered, and the beam stops and the next shape is formed and beam comes on and delivered. So it is step and shoot, and between when the shape is being made, there is no radiation, right? So the beam is off while the leaves move. Sequence of irregular subfields, linear or aerial implementation. Sliding window is beam on while the leaves move. The radiation beam is on while actually the leaves are moving. I will tell you the advantages of this also. I will show you how it works actually. So the velocity of the leaf motion is also important. If it moves faster, you will get a different dose distribution. If you move slower, you get a different dose distribution. Let us look at some scenarios. For example, first we look at step and shoot. For example, I will look at in 2D, it's like 1D and then in 2D I will show you. I call it 1D because we are looking at only one dimension here. Let me say I want a fluence where here it is 3 mu or 3 centigrade, here it is 4 centigrade, here it is 2 centigrade, here it is 5 centigrade, here it is 4 centigrade. I want to generate a pattern like this, right? How do I create segments for segmented IMRT is the question. Like I split this into like A1, A2, A3, A4, B1, A5, A6, A7 and B1, B2, B3. Now B1, B2, B3 are where I'm not going to give any radiation, and A1, A2, A3 or A4 and all we will have to give radiation to get this shape. So this is the profile that I have got. Now here I have to give actually 2 mu or 2 centigrade, 3 mu or 3 centigrade, I'm sorry. Here I have to give 2 centigrade. Suppose if I keep it fully open and give 3, here it will become 3. But here I should not get 3, I get only 2 here. So what I will do is I will close rest of the things and bring my ML leaf to this point and deliver 2. I will have up from here to here up to here, sorry, I can take the leaf up to here and deliver from here to here. I will have 2, or even I can just open it and from here to here the complete thing I can deliver 2. So we have to decide how the segments are done. Let's look at first one. I deliver 2 here and I have opened only up to here, right? It is possible to open it completely and completely deliver 2 also. That is one method of doing. So now I have opened only up to here. I delivered 2 mu. I got this. Now what I do is I open it up to here, right? And then I deliver another 1 mu. So I got this. So now I have done 2 segments. One segment up to here, another segment up to here. Now I will go to the third one where I close this because I cannot give anything more. Maximum is 3. I got it. But here I can deliver 1 mu more. Here I can deliver 1 mu. Here I can deliver 1. Here I can deliver 1. Right? So now I will deliver 1 mu. I mean not 1 mu for example. Yeah, 3 to 4. 1 mu. And I get this is done. So all these are done. Only this one is not done. If you look at, I have to deliver 3 mu here, 3 mu here. So how do I do it? I close up to here and deliver, keep this alone open and deliver 3 mu. You can see the leaf will move fast, close this. This is my last 4th segment and deliver 3 mu. I got the profile I wanted. So I delivered first one segment, then one segment up to here, then the 3rd segment. Now I got the 4th segment. In 4th segment, we were able to achieve this. Let us now look at the similar one in a 2D thing, exactly like a Fluence map. Let us assume this is the Fluence map you want to irradiate. It has got various dose levels, like for example, here you want 10 mu, here you want 8 mu, here you want 7 mu, here you want 5 mu, here you want 9 mu and all those. This is the beam's eye view of the Fluence map. So here I use a equation which is called 2 power n, where n becomes the number that is required to have the maximum mu in that fluence, right? So for example, if I say 2 power 4 here, it will become 16. I don't have 16 here. So the next smaller value is 2 power 3. So 2 power 3 is 8 and I have 8, 9, 10 and all. So what I will do is first I will open up where it is 8 mu and above. So I open up this and this. You can, and I deliver this. This is one segment. So I deliver this. What happens is this 8 will become 0. This 9, 8 is delivered. The rest will be 1. Here it will be 2. Here it should be 1. Let us see. We will deliver the 8 mu. So this is the balance I have now. So next, I don't have anything more than 5 mu, 7 mu now. I can't use 2 power 3 because 2 power 3 will become 8. I have my maximum is only 7 mu. So I will use 2 power 2, which is 4 mu, right? So I open up wherever it is 4 and above. I can deliver 4 here, 5 here, 7 here. You can ask me, here there is a 4 and 7, why you are not opening up? Suppose if I open this leaf up to here, then I will be delivering this 2MU also. So I have to now split this into two segments, right? So 5, 7, 4, 4, 4, 5. If I deliver 4MU, so I will have 1 left over here, 0, 0 here, 1 left here, and 3 left here, right? And again 0 and 3 left here. So I deliver 4MU here. This is what I got. Now there are still areas where I have to deliver 4 or above, 4, 7, 5, 4, 5, 7. So I will open this area and now deliver again 4MU. So this is my third segment, please remember, right? One segment with 8MU, two segments with 4MU. So when I deliver the second segment with 4MU, I will have left of 3, 2, 1, 3 and all. So now I don't have anything 4 or above 4. So I'll have to go lower. So I'll have 2 power 1. 2 power 1 is 2. So I will deliver 2MU. So I will deliver to wherever it is 2 and above 2, I will deliver 2MU. So this is 3, 3, 2, 3, 3, 2. You can again ask me what about this? Suppose if I open this 0 will also get toast. So I will not open that, right? So I delivered 2MU. So now I have left over 1, 1, 1, 1, 1 here, but I have to deliver here and here. So I open this segments alone and deliver again 2MU. So now this will become 1, 0, 1, 1, etc. So now I have only 1MU to be delivered. So how do I get 1? 2 power 0. 2 power 0 is 1MU. So I deliver this segment. Again I can't open this because I have zeros here and deliver this, and then I open this area and deliver 1MU. I have 0. So now everything is given. In 7 segments, we achieved it. First, one segment for 2 power 3, 2 segments for 2 power 4, 2 segments for 2 power 2, and 2 segments for 2 power 1, and 2 segments for 2 power 0. So in 7 segments, we were able to achieve this Fluence Mapping. The same concept is used, even now in some step and shoot IMRTs. And one of my students who did a project with me way back in 2007 or 6, she developed a software to deliver this in 2 power and this using this equation. And for the Fluence, she took a photograph and scanned that and converted it into Fluence, and we delivered that in the linear accelerator. That time we had 1 centimeter leaf, and this is what we got. So this is actually my picture. She took my photograph, converted it into Fluence map, and then generated the Fluence map using that algorithm, and we delivered it. So this is, but nowadays I think you get much finer, beautiful images when you do with the 3mm multi-leaf collimators and things like that. Let us look at the last one, which is the sliding window method, right? Now you have all Linux have sliding window, so it should possible to deliver. So let us look at 2 leaves here. One is bank A and bank B. This can move in this direction, this B can move in this direction, right? Suppose I want a profile which goes like this, increasing profile. So what I do is I move the leaf A, keep the leaf B static, as you can see in this animation. As I move the leaf A, I get increasing profile because this part of the beam was open for a long time. So there will be more dose here, and this part of the beam was open for less time. So you get less dose. So you get an increasing profile. You can change the steepness of the profile by changing the velocity and the position of the beam. Similarly, if you want a decreasing profile, how do you do this? You move the leaf B, you close completely, move it, and you get a decreasing profile. So here you have more dose because this portion was open from the moment it started until it stopped. So this portion will get more dose and this will get less dose. So this is a decreasing profile. So you now know how to make an increasing profile and decreasing profile. So either you move the leaf, keep B static, move leaf A, or keep A static and move leaf B. If you want an increasing and decreasing profile, you have to move both at the same time, right? You want a valley. Most of Fluence maps, if you look at, there is a high dose, low dose, high dose, low dose, what we call the valley and mountain, hill and valley like. So let us look at if both A and B are moved at different velocities, what happens? See, there is an increasing profile. Sorry, there is an increasing profile and there is a decreasing profile and there is an increasing profile and there is a decreasing profile. So you should be able to generate profiles like this by moving both A and B with different velocities. Now, how do you get these type of things like steeper positive gradient, faster leading leaf? One is called leading leaf, other one is called the trailing leaf. Slower trailing leaf and faster leading leaf will give a steeper positive gradient. If you want a steep negative gradient, slower leading leaf and faster trailing leaf, right? You should be able to do it. So we will solve one piecewise polynomial with this movement. Let me say I want a profile like this where it is 80 mu here, 100 mu here, 50 mu here, and then again 100 mu here. I want to generate this. Let me see how I do this. First, what I do is I move the maximum u is 100 and here everywhere it is about 50. So what I'll do is I'll bring the leaf here and move the leaf from here to here. You can and deliver the 50 mu. So what has happened because of that is I got this ramp here because I moved this from here to here, right? And this is an increasing profile in the, or you can call it decreasing profile, but I moved B from here to here. But this was completely open. You got a uniform profile here, right? So the next thing what I do is move the B fast to here, right? I have already delivered 50 mu and then deliver another 20 mu to get this up to, sorry, moved it to here. Now you have to do 80 mu. Okay, now I deliver it and I got 80 mu here and added this 30 mu here and I got the 30 mu here, right? So now I have to now do this first and then I will do this one. So if you can look at, I need to give 20 mu here. I can leave 20 mu and then only the ramp starts. Again, this ramp, if you look at, is maximum 20 mu. So next one, I will deliver the 20 mu so that I get this ramp. I'm going to close this and go up to here. Actually, I'm not doing this. I'm not doing this part of it. So I'm doing from here to here. I moved. So I got this increasing profile. And then these are static, fully open, right? So I got this one. Next, we have to get only this one. So there are, only way I can do is this, bring A to here and move A from here to here, right? So I will get a profile like this. Let's look at this. So now I move that, I get a profile. So I got the entire profile that I wanted for 150 mu after 150 mu. But you see the difference. I delivered only maximum dose is 100 mu, but to achieve that, I have to totally deliver because I did it in piecewise. It's a piecewise polynomial. Thank you very much for the patient listening.